Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the May-June 2023 International A-Level. This is the Cambridge 9709. This is paper 1, variant 2, pure mathematics. And here we have a question all about radian measure. So the diagram shows a sector OAB of a circle. So this is a sector of a circle, OAB, with center O. Angle AOB is theta radians, so this is in radians, and OP is equal to AP is equal to X. So this length is the same as this length. This is an isosceles triangle here. Show that the arc length AB is 2x theta cosine theta. Okay, so the arc length is this length over here. That's the arc length, and that's what we have to find. And we should know from our formulae for sectors of circles that the length of the arc of a circle is given by the formula r theta. This is given in the formula sheet. But here theta must be in radians. It can't be in degrees. Okay. The formula that you learned from IGCSE for length of an arc was theta over 360 degrees times 2 pi r. Okay, that's what we learned in IGCSE because we didn't deal with radians in that time. So it was the angle over 360, that proportion of the whole circumference would be the length of the arc. That's where this formula comes from. It's like this is the circumference, the length all the way around the outline of the circle. We want only a fraction of it that the length of the arc makes, and that's the same fraction that the angle makes with the whole circle. Now, when we deal with radians, then 360 degrees is a whole revolution. So that becomes 2 pi, and that's 2 pi r. The 2 pi's cancel, leaving us with this formula here. So that's where this formula comes from, but the theta must be in radians for this to work. You can't have r times angle in degrees. It has to be in radians. Okay, so that means we need to, we've got to show the arc length is 2x theta cosine theta. So the theta, the angle's fine, because we've got to give it in terms of that. But what we need is the radius of the sector. The radius of the sector is OA. Okay, that's what we have to find now. If we find what OA is, then we can answer this question. So how do we find the length of the OA? And it has to be in terms of x and theta, so we don't have to find the actual value of it. Well, there's a couple of ways we could do this. We have this side x and this side x. We could work out what this side is, what this angle is in terms of theta. It would be like pi minus 2 theta, because it's like the angle. This is also theta, remember, because it's isosceles. But then we could use the cosine rule, but I think that would be very complicated, especially you have the angle as, basically pi minus 2 theta. It's going to be complicated. So I think the easiest way to deal with this question is to just drop a perpendicular line from the vertex to the base of the isosceles triangle. If you do that, this will be a right angle, and because this is isosceles, these two lengths will be the same. So we have this right angle triangle over here. Okay, so let's just focus on that right angle triangle. In this right angle triangle, I'm just going to just highlight it so it's clear. Okay, the length, this length here, from there to there is basically half the radius. Okay, so that length is half the radius. So the length from there to there is the radius divided by 2. Okay, and we know this angle, we know this length in terms of x, so we want to find r in terms of x and theta. We can do that because I can use the cosine of theta. This is, this is in this right angle triangle, this is the adjacent side. This is the adjacent side, and this is the hypotenuse. So we can use cosine. So we can simply say that the cosine of theta is equal to the adjacent, which is r over 2, divided by the hypotenuse, which is x. Okay, so I've written in this way because it's a bit easier to deal with. So you're going to have r over 2 times, you can say 1 over x, right? And we want to find what r is in terms of x. So we can say r is therefore, if you multiply both sides by 2x, it's going to be 2x times cosine theta. So that is the radius of this sector. Okay, and we know that that is the radius of this sector. Okay, now so that's what r is equal to in terms of x. Okay, so we know the length of the arc is equal to r times theta, and I know that the radius is 2x times cosine theta, and the theta is just theta. So the length of the arc therefore is going to be 2x cosine theta times theta. So you end up with 2x times theta times the cosine of theta, which is exactly what we had to show. So we know that we've got the right answer there, and there's the answer to part A. Okay, now for part B of this question. So we're asked to find the area of the shaded region APB in terms of x and theta. We've just worked out that the radius of this sector was, as we just found, 2x cosine theta. So this was the radius, 2x cosine theta, right? So we need to find this shaded area. Now, if you think about it, the shaded area is going to be the area of the whole sector minus the area of the triangle. The area of the triangle APO. Okay, this triangle here. If I find the area of the whole sector OAB, okay, and take away the area of the triangle APO, I will get the shaded area. Okay, so this is the required area, the shaded area. Okay, the shaded area. So for the area of the sector, now we know that the area of a sector is given by the formula a half r squared theta. And again, it's derived from the area of a sector in terms of degrees, where we take the angle over 360, that fraction of the whole area. So it's pi over theta over 360 times pi r squared. But when we're dealing with radians, then this becomes 2 pi instead. This is now 2 pi. Pi cancels with the pi, so you're left with, basically pi over 2 times theta over 2, times r squared, which is a half r squared theta. So that's where this formula comes from. So this is the area of a sector. So the area of the sector here, in terms of our r is 2x cosine theta. So you have a half r squared theta, and you have minus, and the area of a triangle can be found by the formula half AB sine C. Okay, we're going to apply this formula now. So our r is basically 2x cosine theta. So this is a half times 2x times cosine theta squared times theta, which is just theta, minus, and then there's two options we can use for the, area of the triangle. We need to have two sides and the angle between them. So we know this angle is theta. We know this side is x. We know this side is 2x cosine theta. So we could just use those, what we have already. So you get a half times x times 2x cosine theta times the sine of the angle theta. Right? So this will basically give us the expression that we need. Okay, so that will be just simplified. First we have to square this bracket. That's going to be a half times 4x squared cosine squared theta times theta minus, that will cancel with that. You're left with x squared cosine theta sine theta. So when you simplify this, you'll get a half times 4, which is 2 x squared theta, 2x squared theta times cosine squared theta minus x squared times sine theta cosine theta. You'll understand later on why I'm writing this in this way. You can write it either way, but I'm writing it for this way. You won't appreciate it maybe this year, you might next year. Okay, so that is one expression which is perfectly fine for the area of the shaded region. Now there's also something that we could have done alternatively if we wanted to, and it would be perfectly fine. And I'll show you how that works. Okay, so what we could have done, this part would have been the same. Okay, so you'd have got basically the same thing for the area of the sector. So you'd have still got 2x squared theta cosine squared theta for the area of the sector. But for the triangle, we could have used this and this angle, which would be pi minus 2 theta, because this is theta, this is theta. So the three angles add up to 180, and 180 is pi radians. So pi minus 2 theta would be this angle, because we have to have that angle in radians. So we can use a half times x, half AB, so x squared, times the sine of pi minus 2 theta. Okay, if you look at the answer like that, you would get the answer correct. But there's a little point here which I'm going to make, which you might not appreciate right now, but you will when you get to P3. Okay, that we know that the sine of an angle the sine of an angle is equal to 180 minus that angle. So for example, the sine of theta is the same as the sine of 180 minus theta. The sine of 30 is the same as the sine of 150. The sine of, for example, 60 is the same as the sine of 30. So basically, the sine of 60 is the same as the sine of 120. Because we know the sine curve, when it goes like this and comes back down again, the angle over here and the angle over there give us the same sine ratio. So this angle is, this angle here is basically 180 minus the angle there. They give you the same sine ratio. So if that's 30, that would be 150. If that's 60, that would be 120. If that's 80, that would be 170. Add up to 180. So the sine of an angle is always the same value as the sine of 180 minus the angle. So in this case, we could also write this as half x squared times the sine of 2 theta. Okay, and one of the things that we're going to learn next year is the sine of 2 theta can be written as 2 times sine theta cosine theta. All right, so if you take this half sine 2 theta, that will be written as basically 2 times a half. The half will be gone, and you will end up with sine theta cosine. So this and this are exactly the same expression. They have exactly the same value, okay, by identities, which you'll learn next year. So if you get your answer and leave it like this, or like this, or like this, all of those will be acceptable. There's different ways that if you look at the mark scheme, all of these ways are acceptable ways for us to write an answer. So there is the area of this shaded region. I went into a bit more detail just to explain a few things. Was there a part C to this? No. Okay, so that is the end of the question. Other questions from this particular paper can be found in the playlist, which you will find linked in the top of the screen at the end of the video. Other questions from the topic of radian measure from my P1 of Cambridge collection can be found in the playlist over here. And radian measure from my P2 edXL collection, you'll find that in this playlist over here, and you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.